Welcome to Course 4, Module 3, Chapter 8, on reverse logistics networks and the strategic decisions behind them. We will treat reverse logistics as a complex operating system linking collection, testing, recovery, transport, economics, and customer behavior. The chapter shows why circular economy goals depend on strong reverse network design and consistent execution. We will cover operational barriers, operations research models for take-back infrastructure, 3PL roles, triage and recovery routing, and the economics of return flows. By the end, the key message should be clear. Reverse logistics becomes profitable when operational execution and strategic decision models work together. This agenda outlines the learning path for Chapter 8. We begin with the main barriers, enablers, and research gaps that explain why implementation is difficult. We then review operations research models for take-back collection infrastructure, including where returns should be collected and who should manage them. Next, we examine third-party logistics providers in reverse flows. The middle of the chapter covers triage, testing, and routing among recovery options. Finally, we discuss transport cost versus residual core value, plus incentives that encourage timely end-of-life returns. The conclusion integrates these decisions into one reverse logistics logic. This section introduces reverse logistics as a circular economy challenge. The focus is on uncertainty, capability gaps, governance, integration, and the conditions required to make reverse logistics profitable and operationally reliable. This slide summarizes 4 recurring barriers that appear across the reverse logistics literature. First, process uncertainty makes planning difficult because firms often do not know how many products will return, when they will arrive, or what condition they will be in. Second, capability gaps matter because qualified personnel, technical knowledge, training, and organizational awareness are often limited. Third, policy and market conditions can slow implementation when regulations are unclear, incentives are weak, or secondary markets are not mature enough to absorb recovered materials. Fourth, integration failures create friction when information does not flow across manufacturers, retailers, logistics providers, recyclers, and customers. Together, these barriers explain why reverse logistics requires coordinated strategic design, not only operational effort. These categories also overlap in practice. The central operational challenge in reverse logistics is uncertainty, and this uncertainty compounds across decisions. Quantity uncertainty asks how many units will return, which affects capacity, labor, transport, and inventory planning. Quality uncertainty asks what condition those units will be in, which determines whether they can be reused, repaired, remanufactured, recycled, or disposed of. Timing uncertainty asks when returns will arrive, which affects responsiveness and the ability to preserve residual value. Each uncertainty interacts with the others. A large batch of low-quality products arriving late creates a very different decision problem than a small batch of high-quality products arriving quickly. This is why robust network models and decision support tools are so important. That interaction creates the need for structured decisions. Despite these difficulties, reverse logistics can improve performance when the right enablers are present. Information transparency reduces uncertainty and limits inventory and order variance problems. Shorter remanufacturing lead times improve responsiveness and reduce working capital tied up in returns. Industry 4.0 tools, including IoT, automation, data analytics, and blockchain, improve traceability and execution speed. High-quality reverse logistics services also create customer value because returns and recovery shape the customer experience. Closed-loop supply chains can outperform forward-only systems when information, speed, coordination, and technology are designed together. These enablers turn recovery from burden into capability. This slide separates established research themes from areas needing more attention. Current literature covers barriers and enablers, network design, simulation optimization, sustainability performance, and applications in retail, construction, pharmaceuticals, and digital commerce. These themes show that reverse logistics is a mature research area. Important gaps remain: more empirical profitability analysis across industries, more micro-level evidence from developing regions, and better integrated assessment of financial, environmental, and social outcomes. Another gap is the under-quantified impact of reverse logistics service quality on customer outcomes. Research has mapped the problem, but stronger evidence on implementation results is still needed. This section explains how operations research supports take-back collection design by answering where, when, how, and by whom returned products should be collected, routed, and recovered. Operations research helps managers convert take-back design into explicit decision variables and constraints. The first decision is where returns should enter the network, such as retail stores, dedicated collection points, or return centers. The second is when collection and routing should happen, because timing affects both cost and residual value. The third is how products should be collected, for example through drop-off points, mail-back systems, mobile collection, or hybrid nodes. The fourth is by whom the activity should be performed. Different channel choices create different costs, incentives, and control levels. Most models aim to maximize profit while satisfying customer access requirements, regulatory rules, capacity limits, environmental targets, and trade constraints across the reverse network. This makes modeling a bridge between strategy and execution. This slide highlights the range of collection infrastructure options. At one end are physical models, such as retail drop-off points and dedicated collection centers. These give customers visible return locations but require investment in facilities and coordination. Hybrid models combine physical nodes with third-party logistics partners, allowing external providers to collect, transport, remanufacture, or manage parts of the reverse network. At the low infrastructure end are virtual concepts that use e-commerce platforms, online maps, or existing delivery vehicles to collect returns without building a large dedicated network. The managerial takeaway is that infrastructure is not one single design. Firms can choose between capital-intensive, outsourced, hybrid, and digitally coordinated approaches depending on product type, geography, regulation, and customer convenience. Each option involves trade-offs. Several model families support physical reverse network design. Mixed integer programming and mixed integer linear programming optimize collection effort, recovery capacity, product mix, and flow assignment. Multi-objective models extend this by balancing profitability with customer service, trade requirements, and environmental outcomes. Multi-echelon models connect network layers such as retail locations, collection points, processing centers, recovery facilities, and secondary markets. Bi-objective green closed-loop models add explicit trade-offs between total cost and carbon emissions. Each model family captures a different level of complexity. As networks integrate, models must represent economic and environmental objectives across interconnected facilities and guide investment choices. A major strategic question is who should perform collection. If the manufacturer collects products directly, it keeps stronger control over cause, quality information, and recovery strategy, but must build internal infrastructure and management resources. Retailer drop-off uses existing customer access and store networks, yet it can affect pricing, competition, and coordination with forward sales. Third-party logistics or hybrid collection shifts execution to specialized providers and can combine regional collectors with remanufacturing or recovery capabilities. The choice changes incentives, costs, compliance options, and bargaining power. Collection is therefore a strategic design choice for the whole closed-loop supply chain. Integrated reverse logistics models combine location, allocation, routing, inventory, and capacity decisions. The flow usually starts with customers and moves through collection points, return or repair hubs, recovery facilities, and secondary markets. At each stage, managers decide where facilities should be placed, which customers or collection points should be assigned to which centers, and how trucks should be routed. They must also coordinate manufacturing and remanufacturing capacity, inspection assignments, inventory effects, and cost emissions trade-offs. Integrated modeling avoids solving decisions separately. A cheap location may create expensive routing, and routing may fail if recovery capacity is insufficient. Smart collection concepts reduce dedicated infrastructure but require stronger coordination. Mobile collection points can use existing delivery vehicles to collect e-waste or other returns with minimal route deviation. Urban collection and delivery points improve customer convenience, while changing local demand patterns and requiring careful network design. Online and offline return routing models coordinate deliveries with pickups, especially in retail systems where customers expect speed and convenience. The managerial message is that low infrastructure collection works when digital coordination, routing algorithms, and consumer convenience are designed together. Otherwise, smart collection simply shifts complexity from buildings to information systems and planning. The role of 3PLs in managing reverse flows. These providers execute, coordinate, and optimize reverse flows, often becoming strategic orchestrators and sustainability enablers in closed-loop supply chains. This slide emphasizes that 3PLs are not just transport handlers. In reverse logistics, they may manage collection, warehousing, transport, disassembly, and recovery for end-of-life goods, warranty returns, recycling flows, and stock balancing returns. They also coordinate manufacturers, recyclers, remanufacturers, and recovery partners. To do this well, they need strong information systems, financial resources, managerial capability, and technology investments. In closed-loop supply chains, a capable 3PL can improve responsiveness, reduce waste, lower energy use, and support circular economy targets. The shift is from outsourcing one activity to relying on the 3PL as an orchestrator of reverse flows. Embedding a 3PL changes the optimization problem because the provider becomes part of the network design. Models must now decide facility locations, inventory levels, vehicle utilization, capacity, disassembly operations, and recovery flows from the perspective of an external or specialized operator. In some closed-loop supply chains, the 3PL acts as the central network manager and coordinates incentives that increase return rates. For example, pricing or acquisition incentives may be adjusted to encourage consumers or channel partners to return more products. Technical constraints also matter, such as disassembly line balancing or recovery capacity. Therefore, adding a 3PL is not just a contracting decision. It changes the structure, objectives, and constraints of the entire reverse logistics model. The provider becomes part of the optimization logic. Selecting third-party reverse logistics providers requires a broad evaluation framework. Cost and capacity remain important, but the literature increasingly emphasizes the triple bottom line. Economic criteria examine costs, financial performance, and operational capability. Environmental criteria consider emissions, recycling performance, and contribution to circular economy goals. Social criteria include labor practices, community impact, and wider sustainability responsibilities. Risk and reliability criteria evaluate service quality, delivery risk, and consistent performance. Researchers use methods such as fuzzy Swara-Kopras, rough set Topsis or VICOR, interval BWM Markov models, integrated frameworks, and DEA benchmarking. Provider selection must go beyond price to include sustainability and operational resilience. Coordination mechanisms are needed because 3PL effort, reliability, and risk strongly affect total system profit. In dual-channel closed-loop supply chains, some returns may flow through traditional 3PL managed channels while others move through direct online channels. This creates pricing and collection decisions that depend on who leads the channel and how incentives are shared. Reverse auctions allow fourth-party logistics providers to select 3R while considering both cost and delivery risk uncertainty. Contracts can also use incentives and penalties to reward reliable effort and discourage poor performance. The broader governance lesson is that outsourcing reverse logistics does not remove managerial responsibility. Firms must design contracts that align operational risk, sustainability criteria, service quality, and profitability across partners. Governance turns outsourcing into coordinated value creation. Fast, cost-effective triage and testing of returned goods. Returned goods vary widely in condition, so structured workflows, quality grading, and targeted inspection are needed to make fast, cost-effective disposition decisions. Returned goods arrive with very different conditions, and triage protects both value and speed. Some items may be almost ready for resale, while others require repair, disassembly, recycling, or disposal. If all products are treated the same way, firms waste time and money on unnecessary handling. The immediate triage question is disposition. What is the best next step for this unit, given its condition and expected value? Fast triage prevents bottlenecks in warehouses, reduces excessive inspection and movement, and preserves residual value before it decays. The chapter emphasizes that triage is not a minor administrative task. It is a core operational capability that connects physical inspection with economic recovery decisions. Effective triage therefore protects both service levels and profitability. That makes it a strategic operating step. A formal triage workflow replaces ad hoc return handling with a clear sequence of decisions. The first step is receiving, where the item is registered and a high-level condition check is performed. The second step is inspection and evaluation, where physical and functional tests assess quality, usability, and recovery potential. The third step is disposition execution, where the item is routed to reuse, repair, remanufacturing, recycling, or scrap. This structure shortens total process duration and improves customer response time because employees are not reinventing the decision process for every return. Standardization also reduces human error and improves data quality. In reverse logistics, speed and consistency are just as important as technical inspection accuracy. This workflow also supports clearer accountability across teams. Quality grading makes inspection more targeted. High-quality cores may need minimal processing and can move quickly toward resale, reuse, or light refurbishment. Medium-quality cores may require selective repair or deeper evaluation. Low-quality cores may be better for disassembly, recycling, or disposal. This logic prevents every item from going through the same expensive process. Certainty of product quality, or CPQ, strengthens grading by using IoT data, usage histories, and product information before dismantling begins. With reliable usage information, inspection becomes shorter and more algorithmic. CPQ supports faster go or no-go decisions while reducing unnecessary testing effort. Testing intensity is an economic design choice because more inspection usually improves information but also increases cost and delay. Lot inspection sampling offers one solution. Instead of testing every item, firms inspect a calculated subset to infer the quality of the entire lot. This can maximize profit, reduce destructive testing, and avoid wasting effort on clearly defective batches. In other situations, 100% screening may be necessary, especially when compliance, warranty standards, or quality assurance require every unit to be inspected. Then the shipment structure and transport plan must be optimized to control cost. The practical balance is speed, accuracy, and inspection expense. Good triage does not mean testing everything. It means testing enough to make reliable decisions. Managers must choose deliberately. Decision models for routing return products among recovery options. After triage, firms choose the path that best balances condition, demand, capacity, cost, and residual value. Item-level routing models convert condition information into recovery decisions. The incoming core is assessed through observed quality, expected demand, available capacity, and anticipated residual value. Markov decision process models can evaluate whether the unit should be refurbished, harvested for parts, or recycled over multiple periods. Because full MDP models can be computationally complex, linear programming approximations are often used to create dynamic bid price controls. The logic is simple. Accept a recovery option only if its marginal value exceeds the opportunity cost shadow price of using limited capacity or resources. This helps firms avoid processing products that look useful but actually reduce total profit. Item-level models therefore bring economic discipline to disposition decisions. The model protects scarce recovery resources from misuse. This improves both speed and profitability. Network-level models route return flows under severe uncertainty. Instead of deciding one unit at a time, they determine how volume should move through reuse, refurbishment, remanufacturing, recycling, spare parts, or disposal pathways. The uncertainty is substantial. Managers may not know return quantity, return quality, or even the exact bill of materials available from returned products. Two-stage stochastic mixed integer linear programming and related network design models help decide optimal flow volumes while balancing cost, carbon emissions, capacity limits, and quality thresholds. These models are especially useful when returns arrive across regions or countries and when different facilities have different capabilities. They show that recovery routing is a system-wide allocation problem, not merely a local inspection decision. Uncertainty makes optimization especially valuable in this context. Strategic models compare recovery modes and their market consequences. Pure refurbishment can be attractive because it often requires less processing and returns products to market quickly when quality is sufficient. High-quality remanufacturing requires more intensive recovery but may create products that compete more directly with new OEM production. A mixed approach can split returns between lower intensity and higher grade recovery paths, maximizing profit under certain demand and quality conditions. Competition also matters. OEMs, independent remanufacturers, and refurbishers interact strategically, while quality requirements and recovery costs shape viability. Recovery mode selection affects market positioning, not only operational cost. The following section highlights the economic trade-off in reverse logistics. Recovery is profitable only when residual core value outweighs collection, transport, processing, and operating costs. The economics of reverse logistics can be summarized through a margin logic. System profit equals revenue from recovered products and secondary materials minus fixed costs, processing costs, transport costs, and other operating expenses. If recovered revenue is higher than these costs, the reverse network can create financial value. If costs exceed revenue, the system becomes unprofitable even if it has environmental benefits. This is why many models include sensitivity analysis around transport cost, processing cost, return rates, and recovered material value. In some cases, subsidies or financial support may be needed to make socially desirable recovery economically viable. The central point is that circularity must be evaluated with both sustainability goals and realistic cost structures in mind. Profitability requires both value and cost discipline. Transport channel choice depends strongly on how quickly residual value decays. Some products, such as high-tech electronics, lose value rapidly because technology changes, customer demand shifts, or components become obsolete. For these products, paying for a faster and more expensive return channel can be justified because speed preserves residual value. Other products lose value more slowly, so firms can prioritize lower-cost transport even if returns take longer. The decision is therefore not simply whether fast transport is good or bad. It depends on the relationship between transport cost and value decay. Managers should match the reverse channel to the product's economic life cycle, using fast channels when time destroys value and slower channels when cost efficiency dominates. Timing therefore has direct financial consequences. Behavioral incentives for prompt end-of-life product returns. Reverse networks depend on timely end-of-life returns, so incentives must combine financial rewards, convenience, social norms, and emotional or moral motivators. Prompt returns require more than monetary rewards. Financial incentives such as cash, trade-in value, cashback, discounts, and reliability-based rewards can accelerate participation, especially for valuable stored devices. However, convenience is equally important. If consumers face unclear channels, long travel distances, or complicated procedures, they may delay returns even when rewards exist. Social and moral norms also influence behavior, because awareness, perceived duty, and perceived control can motivate returns beyond economic gain. Emotional rewards, such as charity-linked donations, can help overcome frugality and attachment to products. The main message is that incentive design must be holistic. A strong program combines the right financial offer with low friction and behaviorally informed motivation. Together, these levers improve both timing and participation. Design must address both economics and psychology. To conclude, the practical message is that reverse logistics should be managed as a strategic capability, not an afterthought. First, prioritize return streams where residual value, volume, and customer access make recovery economically meaningful. Second, triage products early, because every unnecessary movement increases cost and can destroy recoverable value. Third, align partners around the same measures: cost, speed, service quality, and sustainability performance. That includes 3R, suppliers, repair hubs, recyclers, and internal teams. Finally, test the return experience itself. Convenience, transparent rewards, and social norms can improve participation when money alone is not enough. Coordinated execution helps the network recover more value while supporting circular economy objectives across the product lifecycle. Thank you for your attention. Next, we continue with Module 3, Chapter 9.